Okay, class, this is our first lesson, lesson 1, science skills. It's going to be the same lesson for junior lab rats and lab rats. Now, lab rats, you have had some reading to do prior to the beginning of this lesson. Junior lab rats, you will be watching this lesson in place of reading this week. You will need to have, everybody will need to have your binder and pencil ready. For lab rats, a lot of this will just be checking that you filled in correctly as you did your reading. And for junior lab rats, you'll be filling in as we go along. So a lot of this will be familiar because some of it was included in the pre-lesson that we had, the supplemental lesson 1, and that was required for all new students and recommended for returning students. Some of it was covered in the Grill and Chill. I just want to make sure that we really nail this foundational stuff down before we begin learning new concepts for physical science. So here's some quick tips on how to do your science coursework. This week's lesson and next week's lesson for junior lab rats are video. Most lessons will be in your book. So these green boxes are going to be most of the blanks in your binders. Before class each week, you will need to complete your lesson and binder work before you begin. Have your binder and pencil ready. Read over your binder work assignment before you begin so you know what to be looking for. With your binder work open, you should follow along with your lesson or video by reading in your book, on video or by reading in your book, and fill in the answers in your binder work assignment as you go. If you miss an answer, backtrack to see if you can find it. During class, you will have an opportunity to share your answers. After class, go to Teacher Ease and complete the homework binder work assignment, which is abbreviated with an HW/BW, located in your Teacher Ease assignments under your lesson 1. Remember that the first question is going to be my trigger to grade you for binder work, so it is usually kind of a silly question that has nothing to do with the lesson itself, and the questions that follow it do. I think this week's question is, what's your favorite color? So what's science? Again, let's define science. We did this in our pre-activity, but let's do it again. So Google defines science like this: the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. So let's break that down into simpler terms. And you guys have seen this before. So your intellectual, mental, encompassing, surrounding, structure, construction, physical, touchable, observation, watching, and remember I said before, observation does not necessarily mean visual. It can be anything involving your senses. Practical is hands-on, systematic, organized behavior, actions, natural, real, and experiment testing. So we can take that same definition and say the mental and hands-on activities surrounding the organized study of the construction and actions of the touchable and real world through watching and testing. Or more simply, the study of the natural world through knowledge about the natural world based on facts learned through observation and experiment. All right, so science is a system of knowledge and a method you use to find knowledge. Science often begins with curiosity and ends with discovery. Describing science. So we have branches of science. This year we're studying physical science, but we have the formal sciences, which include mathematics, logic, and statistics. The social sciences, which is things like human behavior and societies, which includes anthropology, economics, geography, political science, psychology, and sociology. Then we have our natural sciences, and this includes things like life sciences, biology, zoology, botany, anatomy, and our physical sciences include chemistry, earth science, and astronomy, and we will be touching on all of these this year. So big ideas in physical science are space and time, forces and motion, matter and change, and energy. Perspective and approach. Science and your perspective. Science is, as we said, a process and a body of knowledge. Be skeptical. Ask questions. Believe in the process. So the process we're discussing here is going to be scientific method. And we're going to talk about that in just a little bit. So using a scientific approach. So we have our scientific method, which is an organized plan for gathering, organizing, and communicating information. The goal of any scientific method is to solve a problem or to better understand an observed event. So we have to make observations, and an observation is information you obtain through your senses. In forming a hypothesis, we talked about this too in our pre-lesson. So a hypothesis here is a proposed answer to a question. It must be able to be tested, it must be either supported or rejected, and it must be repeatable. You're going to want to remember those little bits about a hypothesis like forever. Those are very important. Using a scientific approach, testing a hypothesis. So we have what's called an independent or manipulated variable. We usually call it independent in this class, but some textbooks will refer to it as manipulated variable. Can be manipulated by the experimenter and can cause a change in another variable. So this is basically what you change. Then we have dependent or responding variables. Typically we will use the term dependent variable. And this can change if other factors change and can change in response to a manipulated variable. So this is what you observe for changes. And then we have a control, which is a standard for comparison. And this is what you keep the same. A controlled experiment is an experiment in which only one variable, the manipulated or independent variable, is deliberately changed at a time. And that's another very important one to remember. Using a scientific approach, again, drawing conclusions. If your data doesn't support your hypothesis, you may revise or rewrite it and conduct a new experiment to test the new hypothesis. Developing a theory. A scientific theory is a well-substantiated explanation of some aspect of the natural world that is not yet verified, but that, if true, would explain certain scientific facts or phenomena. Phenomena would be the plural of phenomenon. Scientific law is a rule or principle that always works the same under the same conditions. A scientific law describes an observed pattern in nature without trying to explain it. Scientific theory versus scientific law. The simple way to remember, a scientific law tells what happens and a scientific theory tells why it happens. A scientific law describes an observed pattern in nature without trying to explain it. The explanation of such a pattern is provided by scientific theory. And this is one you've got to remember. If you can remember that a scientific law explains what happens, a truth, and a scientific theory explains why it happens, an explanation, anytime that question gets asked on a test, you'll get all your full credit for it. So this is an example of a scientific theory. This is the theory of spontaneous generation. It wasn't all that scientific. And it has since been disproven, but it's still an interesting little bit of science history.
Long ago, it was believed that living creatures originate spontaneously from the non-living matter. Although there was no scientific theory supporting spontaneous generation, people have developed this concept by their routine observations that occur around them. Aristotle was the first one to record his observations on spontaneous generation. He described about the formation of maggots from decaying meat and sudden appearance of rats from stored grains, etc. However, his concepts were remained unchallenged for more than 2,000 years. In 1668, Francesco Redi has disproved the theory of spontaneous generation for the first time. His experiment has demonstrated maggots arise from flies, not from the decaying matter. After the discovery of microorganisms by Leeuwenhoek in 1676, the arguments on spontaneous generation has taken a new turn. Many scientists have proposed theories which revealed microorganisms arise by spontaneous generation, although larger organisms did not. Later, there were many experiments and arguments on spontaneous generation. In 1748, John Needham had observed microorganisms in heated meat broth, which were not present at the beginning of the experiment. He concluded that the bacteria has originated from the meat. At the same time, Lazzaro Spallanzani has further improved Needham's experiment. He boiled the meat broth and completely sealed the flask, and the microorganisms did not grow. He concluded air has carried the germs to the broth. Theodore Schwann passed the air into a flask containing broth through a red-hot tube. The broth in the flask has shown no growth. Simultaneously, in 1850, George Frederick Schroeder and Theodore von Dusch have allowed air into the flask by passing the air through a sterile cotton plug. No growth was observed. They said the microorganisms from external environment were trapped by the cotton fibers. The usage of cotton plugs to avoid microbial contamination exists even today. Later, in 1861, Louis Pasteur has completely disproved the spontaneous generation concept by his swan neck experiment. Let us go through these experiments.
So here is another example for you. This one is an example of a scientific law. This is Newton's third law, which is that every action has an equal and opposite reaction. I want to hang out with that guy. He looks like a really fun science professor. So now let's move on to scientific communication. So, data are the information gained from observing and testing an experiment. Scientists use data to gain understanding and make conclusions. Scientists often use graphs or tables to show their data and research findings. And as you know, data is plural, datum is singular. So presenting scientific data. First, we have to organize our data. Scientists can organize their data by tables and graphs, communicating data. Scientists can communicate results by writing in scientific journals or speaking at conferences. And then they can use models. And of course, a model is a representation of an object or event. And they make it easier to understand things that might be too difficult to observe directly. And then, of course, we have things like data tables, line graphs, bar graphs, circle graphs. Direct proportion, which is the ratio of two variables, is constant. Inverse proportion. This is the product to two variables, is a constant whole. So basically what that means, let's just say this. When it gets hot outside, I sweat. Those things are directly proportional. The amount which I sweat is directly proportional to the rise in temperature. Inversely proportional would be the opposite. For example, let's see, what's a good one? The colder it gets outside, the higher temperature I set my thermostat. So when it gets colder out there, I make it warmer in here. Those are inversely proportional. So what's this scientific method about? Okay, so who came up with this idea? Well, it's not like it's just one person, actually. There were lots of people who contributed to the concepts. So first we have Aristotle. We just talked about him again. So his inductive, deductive method used inductions from observations to infer general principles, deductions from those principles to check against further observations, and more cycles of induction and deduction to continue the advance of knowledge. Now we have this guy. I'm going to say it wrong, I think, but it's Ibn al-Haytham, and Aristotle was 384 to 322 BC. This fella is 964 to 1040, and while Aristotle was Greek, al-Haytham was in the area of Iraq, Egypt, and Arabia. His scientific method involved following stages, so observation of the natural world, stating a definite problem, forming a robust hypothesis, testing it through experimentation, assessing and analyzing the results, interpreting the data and drawing conclusions, and then publishing findings. And these are very, very similar steps to the modern scientific method, and you'll see a lot of this in your lab work this year. And they became the basis of Western science during the Renaissance. If you're unfamiliar with this concept, This fellow is a Muslim, and in Islam, the gaining of knowledge is very important. It's something they hold in high regard. There are actually a lot of scientists from this time period and this part of the world who made it just their vocation to continue to learn. And we've also got Sir Francis Bacon. He's an English dude. And now we're in the 1600s. So in order to test potential truths or hypotheses, Bacon devised a method whereby scientists set up experiments to manipulate nature and attempt to prove their hypotheses wrong. And then we have Galileo Galilei, and you probably know who he is. So he was living in around the same time period as Bacon. Galileo pioneered the experimental scientific method and was the first to use a refracting telescope to make important astronomical discoveries. He's often referred to as the father of modern astronomy and the father of modern physics. We are actually going to test Galileo's hypothesis in a lab this year. It's a particular hypothesis. And Galileo is the fellow who recognized that the Earth revolves around the sun and not the other way around. Science and technology. What's technology? Technology is the use of knowledge to solve practical problems. Science and technology are interdependent, meaning one relies on the other. So, technology can be anything from the pencil in your hand to the latest and greatest in computers. So, measuring. And this was in the pre-lesson, so we'll just go over it quickly. Measurements can be made in non-standard or standard units. Now, what this means is, say you want to measure using a ruler, that would be a standard unit, but you could also measure things with your pencil. You could measure things with your foot, like paces. We talked about that in my pre-lesson, where I was giving you hints to my favorite movie. And then scientific notation. In the U.S., we commonly use imperial or standard customary system, but in science and in most other countries, the metric system is used. Scientific notation is a way of expressing a value as a product of a number between 1 and 10 and a power of 10, and it makes very large or very small numbers easier to work with. And then SI units, of course. If we didn't go over this before, SI stands for Système International d'Unité, and it is a revised version of the metric system. And this is where we get sort of the perfected methods we use today. So our units. Scientists use a set of measuring units called SI units, or Système International d'Unité, a revised version of the metric system. So let's see, can you guess any of these? What do we use for length? Meter. How about mass, or how much matter there is? Grams. Weight, which is the effect of gravity on mass. We also use grams. Area, which is two-dimensional. We use meter squared. Volume, which is three-dimensional. We use meter cubed. You can also use liters in this spot. Density, how much mass is in a contained space. Kilogram per meter cubed. And time, we use seconds. Temperature, we use degrees Celsius. Sometimes you will see degrees Kelvin being used, and that's okay. But we don't typically use Fahrenheit in science, which is what you're used to. So sometimes it can seem a little odd when we talk about room temperature being in the 20-ish degrees area, because that's what it is in Celsius. It's sort of like if you've ever driven in a country like in Canada or anywhere that uses kilometers instead of miles, and it'll tell you to go like 120 kilometers per hour. And when you see that on the sign when you're driving, you're like, woo, but it's really not that fast. All right, so what if we divide by 1,000? Oh, sorry, divide by 10, we get deci. If we divide it by, multiply it times 10, we get deca. If we divide by 100, we get centi. If we multiply by 100, we get hecto. If we divide by 1,000, we get milli. And if we multiply by 1,000, we get kilo. And also note that we have length meter, mass gram, time second, temperature Kelvin, amount mole. This is going to apply to chemistry, not so much in this class, but be aware of it. Electric current, ampere, you'll hear the word amp. I'm sure you've heard amp before. And then luminous intensity is candela. There's a couple others that are used there, but candela is sort of the standard. And we will be talking about current this year. So keep these in mind. So Scientific notation is a way of expressing a value as a product of a number between 1 and 10 and a power of 10. All right, so look at some of these numbers right here. For example, we can say 3 times 10 to the negative 18, that's the top one there. 3 times 10 to the negative 18 grams is oh my goodness, 0.0000000. I've already lost my place. So when we say 3 times 10 to the negative 18 gram, it is much easier to write, much easier to comprehend. Now, I want you to pay close attention to the way these numbers are set up. We have, and then we also, you could call it an addagram. You know, we have kilograms and decagrams and whatever. This case, these are smaller, and once you get past, like if you look in the middle where you see 3 grams, you get decigrams, centigrams, milligrams. Okay, we went over that. The next one would be micro, then nano, then pico, then femto. And if we go the other direction, if we go bigger, we go from grams, deca, hecto, and kilo, which you know. Then we get mega, giga, tera, penta, and exagrams. Woof, they keep going. So notice something about these. It makes large numbers or small numbers easier to work with. But if you notice, we have deci is -1, then we have -2 and -3 up to milli. But then we go -6, -9, -12, -15, -18. And at the bottom, we do the same thing. We have to the first power, second power, third power, and then it goes 6, 9, 12, 15, 18. So what do we notice about this? Well, I chose the number 3 in this example for a reason. Okay, that's why we have 3 addagrams, 3 femtograms, 3 picograms. Do you see that? It's to help you remember a pattern used in scientific notation. So once you get, do you notice the pattern in the exponent? So once you get past centi or deca, which are commonly used, they are all multiples of 3. Now why 3? Okay, I'll show you why 3. Let's put the commas in place. It has to do with where the commas go. So when you write the number like 32,000, you write 32, 000. There's your comma 000. So we separate them by 3's. All right, measurement. Limits of measurement. So precision is the gauge of how exact a measurement is. And the precision of a calculated answer is limited by the least precise measurement used in the calculation, which makes sense. You can only be as precise as your least precise measurement. Then we have accuracy, and that's the closeness of a measurement to the actual value being measured. So this has a lot to do with your instrumentation. What are you measuring with? Is it at all accurate? And then we have significant digit. And this is all the digits that are known in an estimate plus the last digit, which is estimated. And we'll talk about that a little bit more this year, but you don't need to worry about it right now. So our metric prefixes, again, meter, mass, gram, second, Kelvin, like I said, Celsius, sometimes Kelvin, mole, ampere, and candela. And then our derived units, okay, base units, you can see, we don't have any sort of math going on there. We just kind of have a thing. What is time? It is a second. Okay, what is amount? It is a mole. Derived units, you got a little math going on. So we have a square meter, which is a meter squared, 2D. Volume is a cubic meter, that would be 3D. So it would be like liters to the third power. And then we have density. So this is kilograms per cubic meter. So how much mass is contained in a space. So you can hear that. That is actually a math equation. Kilograms per meter would be kilograms over meters, right? Pressure is measured in pascals, energy in joules, frequency in hertz, and electric charge in coulomb. We will talk a lot about pascal, joule, and hertz later on this year. Instruments of measurement, we got lots of them. These are just some things that you might measure with. And you may recognize some, there might be some you don't recognize. And we will use some of these instruments in labs this year. In the lab, working safely in the lab, always follow safety rules, teacher's instructions, and lab directions in the lab. This is going to be your lab assignment for this week. It is a lab safety assignment. Since we won't be in the physical lab, you will be learning how to be safe in lab. So that's the end of lesson 1. So what you need to do now is complete your lab. It's located in your binder, but the actual assignment for credit is in Teacher Ease. So once you work your way through what's in your binder, you know what to do next. You need to complete your homework binder work. Now, we usually do not have a homework assignment the same week as a test, but since this is our first week of class, I wanted to keep our typical pattern of lesson, homework, lesson, homework. So it's a quick homework assignment, and the unit test is actually not too long either since it's only one lesson. So you're going to want to study for your Unit 1 test. The study topics are going to be on this last slide that's going to follow, as well as in your student Dropbox. You're going to complete your Unit 1 test in Teacher Ease and then begin Lesson 2. Here are your Unit 1 test study topics, and these will be also available to you in your student Dropbox and the resources under Unit Test Study Topics. And so go ahead and study your notes, study your videos, and you'll be good to go for your Unit 1 test, which is due by 8 a.m. on the 22nd. And I will see you on the 22nd when I get back from Texas. Can't wait to see everybody.